Good morning, good afternoon, and good evening, everyone, and welcome to today's Ask the Expert webinar on materials characterization of gallium nitride power transistors. Our experts for today are Dr. Tamel Bayuk-Lamanli, Scientific Fellow and Vice President, Dr. Mike Salmon, Scientific Fellow of Advanced Imaging, and Dr. Miki Nakayama, Team Leader. My name is Rena Samsu, and I am the Marketing Manager assisting with today's event. Before we get started, I would like to go over a few housekeeping items. All attendees have been muted. However, if you have additional questions that come up during the presentation, please submit them in the questions panel located in the bottom right of your screen. You may send in your questions at any time during the presentation, and we will follow up with you in the coming weeks. With the abundance of questions submitted for today's event, we unfortunately will not be able to get to all the questions during the presentation. For any unanswered questions, the team will try to send answers out to those questions in the weeks following. At the end of the webinar, a survey will pop up on your screen. Your feedback is greatly appreciated and will help us to improve our future events. Now I will turn it over to Dr. Alan Wan, who will be moderating today's presentation. Alan?
Thank you, Rena. Okay, so without further ado, next slide, please. We'll introduce you a little bit to EAG for those who are not familiar, giving you an idea of overall overview of all the techniques that we have. Of course, this event is centered on the questions that you have asked on this specific topic, so I'll try to reserve more time for that. Next slide, please. EAG is a global leader. We have labs situated all across the globe, in addition to most of our analytical capabilities being in the US. We have over our network of laboratories, over 1,000 highly educated employees, and basically more than 20 different locations servicing a variety of different techniques. So being a worldwide company, we have over 5,000 countries 5,000 clients in many different countries. We are here to help you wherever you are. Next slide, please. So this is a good summary of all the different techniques that we offer here at EAG. I'd like to emphasize that this particular webinar, it will be focusing on dynamic SIMS as well as microscopy. So if you advance further, you can see the SIMS on the bubble chart actually occupies a significant amount of area. Basically, it is the technique for using depth profiling to get very good detection limits, basically down to almost the most sensitive of all the different techniques that we have, and can also be focused down to a fairly small, not super small, but fairly small spot size to actually analyze reasonably small areas. But not to be forgotten, we also have the imaging techniques. Again, this is both a dynamic SIMS and microscopy webinar. And of course, with the imaging, we can then not necessarily, we will get not as much chemical information, but we will have plenty of information on analyzing small features, for example, all the way down to TEM range. Next slide, please. So when choosing a technique, it is important to understand the depth of analysis and what you need to understand or know. In the case of SIMS, for example, is a depth profiling technique, so it can be tuned to going down to very deep into a substrate, or getting tuned to only a small portion of the surface. So basically, that's why it has an arrow there. But keep in mind that we can also look at using other techniques to look at a variety of different properties. Either way, reach out to an EAG expert who can then help you get situated with whatever technique or techniques that will best answer your question. Next slide, please. So in particular, when we're looking for elemental information through a variety of layers, there are several strategies we can go about doing so. SIMS, of course, being one of them, and we'll be talking about today. But we can also use, for example, Auger or XPS, also in a depth profiling mode, to look at those type of signals coming from those layers. In addition, we can also take a cross-section of a sample and take a look at electron microscopy, or also do AFM, and also examine more of the layer structure in that method. Either way, multiple ways of being able to attack the depth profiling problem, and either way, we can provide you answers with a combination of techniques. Next slide, please. Okay, without further ado, I do want to introduce our main panelists. Next slide. So, of course, first panelist is Dr. Tamel Bayuk-Lamanli, who has over 30 35 years of experience in SIMS. He comes to us from University of Florida, and then he has been with the company for, again, quite some time. He has worked in various different roles in the company, both in the operations group in SIMS, as well as part of our commercial group. He has led several different methodologies, as well as a different type of interface for customers, as well as planning on projects. Dr. Mike Salmon is scientific fellow with Advanced Imaging. He comes to us from North Carolina State, where he has spent basically the majority of his career working on microscopy as well as surface analysis techniques. And he has also been looking on primarily compound semiconductors, although he has also certainly has a wide variety of expertise on many different materials. And then Dr. Miki Nakayama is our team leader. She has joined EAG since 2016. She comes to us from Brookhaven, and she also acquired a PhD from the University of Chicago, again, doing a lot of surface analysis for her career. And so with that, I will pass off to Mel, who will answer our first question of the day. Mel, please go ahead.
Hello, good morning, good afternoon, good evening, wherever you are. So this question that we typically get quite often is in relation to definitions of SIMS. The question was about time of flight SIMS or TOF SIMS versus dynamic SIMS. So to really understand this question and have a good comprehensive answer, let me start with basically giving you an overview of what the dynamic SIMS process is. So we have this crystalline lattice that is getting bombarded by a primary ion beam, and the impact of this beam creates this mixture of atoms. So the escape depth of these ions determines where the atoms are coming from. And that mixing range can be varied depending on the energy of the beam that is hitting the sample. This energy transfer causes the ejection or the sputtering of the particles or atoms or molecules from the surface of the sample, and they can be in ion form or they can be neutral beam. And depending on what they are and what the elements are, we basically detect it in our SIMS spectrometer. The schematic of the instrument is that you have the primary ion beam hitting the sample, and it's rastered in a certain square fashion. And then as this sputtering continues, the surface recedes into the bulk, and the particles that existed at the very top of the surface will get ejected from the surface in forms of neutrals, negative ions, or positive ions. The ones that are charged, or ions, extracted through an electric field and pulled into the mass spectrometer, and then from the specific mass going through the mass spectrometer get filtered and sent into the detector, and the counting system can be detected in electronic format. So if you vary the mass spectrometer to detect all the masses coming in, it comes in as mass spectra. Or if you basically tie the species you're detecting in the mass spectrometer to the location of the crater bottom, you can get a map of a given species. Today, we're going to be mostly talking about a depth profile where we specifically follow species of interest from the surface into the bulk. And this distribution, we call it the depth profile. But there are challenges in doing the SIMS analysis in a depth profile mode. And this basically a simple illustration of how challenging these measurements can be. It's a very thinly doped boron into a silicon material. We all know that the silicon has a surface oxide, native oxide, and that silicon dioxide has a third of the silicon in that layer in comparison to the silicon bulk, which is 100% silicon. But if you track this green curve, which is representing the silicon ion intensity, you see that the intensity goes up. It goes against what you would expect. You would expect that the silicon signal will go down because the composition goes down. And this basically illustrates the complexity of the SIMS characterization, that these intensities doesn't always go in the way that you expect. And sometimes unquantified, uncalibrated SIM signals can be very deceptive, just like in this case. In this particular sample, our goal is not to quantify silicon, it's to quantify boron, and silicon is used as a reference signal. And if your reference signal is not doing what you expect it should do or in proportion to the composition, you would know what to do with the boron. That is the focus of the measurement. But we'll get to how we fix that. So as we have mentioned, this primary ion beam causing these particles coming off, and in ions, either negative ions or positive ions or neutrals. The complication of the previous slide is due to this, the ratio of the ionized particles to the neutrals. Only a few percent, less than 10% of these particles that are coming off the sample gets ionized, and we can only detect the ones that are ionized. And we find that the ionization potential of these particles are very much depending on the matrix they're coming from. So therefore, in SIMS data, if you don't have a proper standard to calibrate the ions that are coming off, you may end up with a very deceptive result. But once you have the standard, and this standard will allow you to calculate the sensitivity factor of a species of interest, with this very simple formula, you calculate the composition of the material at a given data point I. As you recede into the sample, you collect different data points, and they are listed as the I here, the ith data point. The calibration of the horizontal axis in the SIMS, which is the depth, is quite simple as well. You basically, at the end of the measurement, you get a depth measurement and then divided by the total sputter time, and it gives you a sputter rate, erosion rate, or etch rate, whatever you want to call it. We usually call it the sputter rate. So using that sputter rate at data point I, you can multiply it with the sputter time at that data point I, and then it gives you the depth. But the problem, the effect of the matrix changes this sensitivity factor, also changes the sputter rate. So we have to come up with a method to really calibrate the SIM signals based on the change of the matrix. And when you properly do that, example I showed earlier, where you had a very shallow distribution of the boron, we're looking at top 20 nanometers or so, you get the correct shape of the distribution of the boron, even so shallow. When there's a big change in composition from silicon to dioxide and then to hydrocarbons at the very top surface. To address then the question about time-of-flight SIMS or TOF SIMS, I would like to describe to you the spectrometers we use in secondary ion mass spectrometry. There are three types: magnetic sector, quadrupole, and time-of-flight SIMS. All three basically filters out the masses that you want to send to your detector. The magnetic sector, hence in the name, uses the magnetic field to filter out the masses. Quadrupole will use electric field, alternating electric field, to send the masses into the detector. Time of flight, hence in the name, uses the time of the flight from the sample into the detector to determine the mass that is arriving to the detector. So all three can be used in different aspects of the analysis. There are two modes to the SIMS. There's a dynamic SIMS, where you're basically constantly eroding the sample with the primary ion beam. There's constant material removal, and you can only do elemental analysis. You have no information about its molecular imprint that existed in the bottom of the crater. So you can only detect specific species as you go through, and all three spectrometers can be used in this dynamic SIMS mode. But we've usually used a magnetic sector in the quadrupole SIMS when you're doing dopant analyses in multi-layer structures. That gives us the better detection limit and cost effectiveness. Static SIMS essentially looks at the top few monolayers. And instead of having a very energetic beam, you use a lightly pulsed ion beam that only jiggles the surface to eject the species from the very top surface. And that helps us do molecular analysis of these very top surfaces. And it doesn't really sputter the surface. It doesn't really remove material as much as this dynamic SIMS does. And therefore, it's very useful to do organic and inorganic analyses. It's a very good survey technique. It can give you what is present on that surface. So that is the difference between time of flight SIMS or and the rest of the SIMS. We would like to say that it's dynamic SIMS or static SIMS. And luckily at EAG, we have all three spectrometers and multiple redundancies. So we can really pick the right spectrometer for the problem. So the question then, going back to the quantifying the SIM signals for dopants and impurities and how the matrix affects, there was a very good question about how the quantification for the dopants and impurities happen when the composition is changing, when the composition has a gradient to it. You can, if you have distinct layers, you can essentially use one calibrated in one distinct layer and then another calibration, another distinct layer. But if the composition is graded, what do you do? So that will be the topic of the next few slides. And this, as the question brought up, this is a big issue with the compound semiconductors. And over the 20 plus years, we have had customers come to us and saying, well, we, in a compound semiconductor layer structure, would like to measure the dopant abruptness, how the dopants come down at a given layer, where the impurities show up in the epitaxial layer structure, so they can do a failure analysis of these. And the other thing is that the composition that is measured at the same time with the impurities and the dopants sometimes can be very, very thin. In the GaN hemp structures we're going to talk about, the top surface, the barrier and the channel region, and then how you need to quantify these very thin layers to really pinpoint the dopants and impurities together with the composition. And sometimes there are these gradients that you want to measure to a certain dynamic range. All of this is within the realm of the SIMS, but it requires a new thinking, new theory, new way of calibration the SIM signals. And that we call the P-core SIMS, or it's short for point-by-point correction to the sputter rate and RSF changes, so you can get the most accurate data for the depth and the concentration at every data point. And we call that P-core SIMS. So we're going to be showing a lot of P-core SIMS data throughout this event. How do we get there? Basically, a lot of work. You end up with a lot of different matrices that you have to use for the calibration or building a calibration curve, and you implant them with the species of interest. And the assumption you make is that the amount of these species of interest are identical in the substrate that they are being implanted to. And by studying how the ions of these species of interest change with the stoichiometry of the composition, you build a model and then you build a formula, and that helps you to calibrate the SIM signals as the composition changes. And as the bottom, we're going to talk about the GaN materials, AlGaN materials, but the examples, there's one example for the gradient that I'm going to show for the AlGaN structure, which is very illustrative for the graded structures. So when you do that analysis that you've just implanted for, say, carbon and silicon, and you plot it against the change in aluminum content, you see that there's luckily a linear change of the sensitivity factor from 0 aluminum to 100% aluminum. And if you were to use a single RSF where there's no aluminum present in your standard, and to try to quantify, say, 80% aluminum, your error could be close to the factor of 3. That's how bad the SIMS calibration can get to if you don't do proper calibration or proper standard for it. But once you have that calibration curve, you can actually quantify very intricate layers. This is a vertical cavity surface emitting laser DVR layers where you have a graded aluminum, And right at that graded aluminum, you have a carbon dopant. Now, if you were to use a single sensitivity factor, you'll be getting this black curve. But if you were to use point-by-point corrected SIMS, right at this graded edge, you get the correct carbon profile. And as you can see, between the not traditional standard SIMS versus the P-core SIMS, there's a factor of 3 difference. And that is because of this matrix effects that we're talking about. And you can actually do that in very, very thin layers. And we're showing an example for 20 nanometer thick layers. So the next question is, okay, so you have the calibration curve, but you need to do the composition together with the dopants and impurities for the calibration to work. And SIMS, for a very long time, assumed that it was only good for dilute impurities and dopants below atom percent level, and it's not good for composition. But for us to be able to do the P-core SIMS, we knew that we need to develop a new method to quantify the composition together with these dilute dopants and impurities. And this question is quite valid in that, you know, what technique do you use to calibrate these things for InGaN and AlGaN and AlGas, etc. And we either use a NIST standard, or if there's no NIST standard available, we use Rutherford backscattering, the RBS. So one example of that is the AlGas layer structure that we specifically had designed to do the calibration with Rutherford backscattering and P-core SIMS. This changes from 7% aluminum to 80% aluminum. The same thing happens in the AlGaN, but we don't have a very good example that we could use, or we had the permission to show. So, but this one we have. So it's basically the same thing in the nitrides. As you can see, we can measure the aluminum for a very high dynamic range, and the concentrations are within 5%, which is the uncertainty DRBS. So we're now confident we can do the P-core analyses as the composition of the material varies. Now let's get to the topic of the day. As the power transistors come into play more frequently, there was a desire to make them affordable, and GaN hemp filled that void very well, and it became very popular. And there are some information that the GaN hemp epitaxial engineers would like to get out of the structure. This is a very typical GaN hemp structure, and for affordability, it's grown on a silicon substrate, and you have these layers of nucleation buffer to reduce the amount of defects that go in. And then this is where all the action is when you apply the electric field or apply the voltage, and then electrons start moving around. So what the epitaxial engineers would like to get out of this structure is what are the defect densities, especially around the buffer and nucleation, but more importantly, right around here. And what are the impurities that could be present in these layers that will cause leakages? Or what are the dopants you intentionally put to address them? And therefore, the dopants and impurities right around this channel region, right around where the 2DAG is quite important. So we need to build some SIMS protocols just to be able to address that. And the challenge, even in the SIMS, doing the analysis, is that these layers have these dislocations and defects all throughout the epistructure. And some of these, even though these layers are grown to minimize the defects right where the transistor action is happening, some of them make it all the way to the top. This is the surface here, this is your 2DAG region, and these dislocations can make all the way to the top. Well, I'll show you examples of how they affect our SIMS measurement. Now let's look at a SIMS plot of the structure. There's your substrate, silicon substrate, there's your nucleation layer and the AlGaN buffer layers and the channel region. So in this particular analysis, we're concentrating on the impurities or the dopant concentrations in this region. And this is a 4 micron. These days, the thicknesses can go 8 microns. So it's a typical measurement for us for gallium nitride hemp structures. And there's this barrier region and 2DAG region. We basically it's not very easy to decipher. We'll get to that in a minute. But here, again, we're talking about how to do the dopant calibration where the composition is changing. We basically do a comparison of a P-core SIMS calibration versus a gallium nitride RSF. And as you can see, there's a factor of 3 difference in quantification. So you have to do the proper calibration to be able to study these compositions. And when you do that, you can do a comparison of a wafer center to the wafer edge. And as you can see, that there's a big difference in these concentrations across the wafer. So the next question, which is quite important in gallium nitride hemp, is what is the detection limit that you can reach in the SIMS measurements? Can you go down to E14 levels? And for that, I would like to introduce you to the gallium nitride SIMS team leader, Miki Nakayama, to address these questions for you. Take it away, Miki.
All right. All right. So, I guess from here we'll show like a few example profiles with some really good detection limits. I guess move on. So let's see here. We're showing that we can get pretty low silicon detection limits. And then so it's in the E14s. Hydrogen here, it's probably actually like we can routinely usually get like low E17 detection limits. Here, I think the bump in the hydrogen is probably real, and we can see that because of the low detection limit. That's probably where the carbon comes up actually, but anyways. Next here, we show that we can also get low detection limits of iron and boron in the E14, like high E14s. Okay, next. Yes, and here we're also showing we can get very low magnesium detection limits, even in the E13s. And because of this low detection limit, we can actually then detect low dosing levels in the low E15s. Yes, next. So so here we're showing a table of sort of the very typical detection limit values and sort of our best values that we can achieve. But please keep in mind that these are all ballpark values. The detection limit will vary actually quite vastly depending on a lot of things. And I'm listing some factors that affect the detection limit here. So one example will be the chamber cleanliness. Of course, we need to have very good pumping, very good vacuum to get, especially for atmospheric elements. So for example, like oxygen and carbon, that might be limited by what's in the background of the chamber. The detection limit will also depend on the analytical conditions. For example, if we're looking at a deep analysis versus a very shallow analysis. So that would change the sputter rate. And typically, for atmospheric elements, if you're sputtering slower, then you'll get a higher detection limit. If you're sputtering faster, you'll get lower detection limit. Let's see. And then also, it will also be dependent on the material composition. So in GaN case, it's obviously going to be the aluminum percentage. Typically, again, for atmospheric elements, if you have a higher aluminum percentage, then typically you'll have a higher detection limit as well. It's partly also because aluminum nitride's higher aluminum sputters slower. And then also, actually, I guess also to keep in mind, we are using GaN aluminum nitride standards. So if you happen to have like a super high like percent level oxygen or something in there, then that will also start to affect things. Basically, as you deviate from nitride, things will get affected. Also, another thing that would affect the detection limit will be the sample surface cleanliness or the roughness. You can get sort of, what do you call it? If it's super rough or super dirty, things will tail, and that would affect the detection limit adversely. So, if you ever need like certain detection limit values in your analysis, please let us know beforehand so that we can, try to analyze in the best possible way to meet your needs. All right, next. Okay, so next, there's a whole bunch of questions related to layer resolution. Let's see, like from what depth can we resolve like accurately the dopant and impurity concentrations? How accurate are the profiles of the aluminum and gallium in between the barrier and channel? To what extent are they caused by crater effect? So like what is the minimal depth resolution, distinguishing surface effects and bulk effects? I just answered the detection limit, but then there was also, can a thin layer of aluminum nitride be accurately detected? And can the different thicknesses of GaN cap layers be detected? So I will actually pass that back to Tamal to answer.
Thank you, Mickey. So this is a very common question we receive from gallium nitride hemp engineers, researchers, scientists. And we have actually developed a very specific method just to be able to address that. As you can see, when you're doing a profiling, going microns into the bulk of the material, we have to use a very high sputter rate to go through it in a cost-effective manner. But in that mode, we almost get nothing about this top surface. But it is where most of the transistor action is happening. So you need to be able to have some understanding of what's happening of these nanometer thick layers. So when you do a proper calibration, proper sample cleaning, proper SIMS protocol, you can actually get information in that top 15 nanometers. So this basically is a layer of AlGaN on aluminum nitride on top of the GaN channel region, and it's only 15 nanometers, yet we can get signals in this layer for, say, most importantly for carbon. Unfortunately, if the surface is contaminated in some shape or form, there's an oxide or a silicon present, we can minimize but not completely avoid the surface knock-in from into the material. So these tails you see are basically an artifact of that high concentration on the surface with our primary ion beam hitting and mixing it in below. This usually is less of a problem, but the carbon is the interest to most of you. And if you plot it on a linear scale, you can actually get a sense of the GaN cap layer, maybe 1 or 2 nanometers thick. And then there's this 15 nanometer AlGaN layer, and then a couple of nanometer thick aluminum nitride layer. So you basically know where you are when you're measuring the carbons to get an understanding where the carbon comes in. And to really have a good understanding of these layer structures, which SIMS have challenges in properly resolving it, we go to electron microscopy. This is an overlay of that same SIMS data, this time onto a high resolution STEM imaging, and we see the aluminum nitride, we see the GaN layer here, AlGaN layer here. And if you look at the SIMS profile, there's this mixing that comes with the ion beam, and TEM clearly shows there's none of that happening into the GaN. So it's always good to have a secondary method to check on the SIMS, or vice versa. If you're just doing microscopy, then you may not be able to get the carbon and the location of the carbon with these stoichiometries. So it's always best to do both of them. But once you arm yourself with this calibration, with this new protocol, you can actually do quite good studies. And one example of that is studying the impurities and the profile shapes of these stoichiometries from the wafer center to the wafer edge. This shows the carbon profile in that top 30 nanometers, a different sample. And as we all know, the surface always have this adventitious carbon, could be carbonates, carbohydroxides, and so on and so forth. But the most of it is just carbon. So you have to have the specific SIMS protocol to be able to profile these things into this thin layer to get to the background. Once you do that, you when compare it on the same wafer, now this time edge of the wafer, you can actually see a big difference, a factor 2 difference of the carbon. This can only be possible if you do the proper SIMS calibration and SIMS protocol, SIMS calibration. And we see very strange things. There's this carbon peaking at the aluminum nitride algan interface. There's this carbon that presents roughly around where the 2-DAG is, which doesn't exist in the center of the wafer. So with the higher resolution analyses and the pico calibration, you can do studies in nanometer scale, provided that the sample surface roughness is less than the features you're trying to measure, or the interfaces are less, interface roughness is less than the features you're trying to measure. The physical aspect of these films affect the SIMS measurement. And I'm going to show you a few examples of that. Carbon is one, but there's also metallic impurities that people care about. In this analysis, we're looking at iron impurity in that top 30 nanometers. So these kind of things are possible. So the next question is about the effects of the defects, how the depth to which do you go to affect the calibration of these curves, and what do we do for the SIMS calibration when this is happening? One trouble with the gallium nitride ever since the blue LEDs came about is the formation of the defects in these materials, and they come in different shapes or form. This is an example of an LED because I don't have it for gallium nitride hemp, but it illustrates the point that we may run into with the GaN hemps as well. We see a profile of the indium going through the InGaN superlattice, and then there's this magnesium doped algan layer, and we see this shoulder. This shoulder could be an aluminum diffusion from the top layer. It could be aluminum contamination as you're growing the InGaN layers, or it could be a SIMS artifact. To understand what it is, we do microscopy. And in the microscopy, we see that these InGaN layers have a V-shaped voids or defects. And when you deposit the aluminum, aluminum basically fills those voids with aluminum. So these V-shaped places will have now aluminum. When you profile it from the top, you see that when you reach to the indium, in other words, you start seeing the indium signal, there's still aluminum left over in the bottom of the crater because of filling effect of the aluminum. So these shoulders are now an artifact. You can only know that if you do microscopy. There's another problem with the GaN hemps, and that's this defect that goes all the way to the surface that creates this pit. When you do an AFM, you see that these pits are all over the place, and it's very high density of these. And if you do a line scan through it, you'll find that these things can go as deep as 45 nanometers. And if you're trying to do the barrier layer analyses in nanometer resolution, and you have these pits, how do they affect the SIMS measurement? Now think of the same example I gave you in the LEDs, where the aluminum is filling the V-shaped voids. Same thing is happening on the surface of these GaN hemp materials, where these voids are going to get filled with the atmospheric contamination, namely carbon. So when you profile it, just like the aluminum case, you will have this deep going carbon. And if you didn't have this AFM data and you look at that carbon, you would make an assumption that your barrier layer in the channel region has this very high carbon concentration, but it's completely a SIMS artifact of because of the morphology of the epitaxial film. But we have an answer to that as well. We basically do a carbon clean of these pits where the impurities are, and after the cleaning, we can get nice low detection limit carbon in these tens of nanometer layers. So the next question is, how does the depth come into play in the resolving of these layers. And then I'm gonna again pass this on to Mickey, who deals with this thing every day, to explain what might be the problem with these. Your turn, Mickey, again.
Okay. All right. So I mean, basically, I just kind of wanted to re-emphasize that SIMS can only be good as the sample, kind of. So the surface roughness affects the layer resolution a lot. Basically, so SIMS can only clearly resolve layers that are significantly thicker than the total Z height difference of the sample surface, not the RMS roughness. So it's the total Z height difference. Essentially, the rougher the sample, the more tailing and the more broadening you get, as I kind of mentioned before. Also, another thing to keep in mind is that the layer resolution tends to degrade with the depth as you sputter. That's because of crater bottom flatness, or maybe the sample can roughen as you sputter. So something to keep in mind is that if you have sort of a relatively thin layer of interest, it should ideally sort of be towards the top of the sample, towards the surface. If it gets buried, then the features can get broadened. Also, so for samples, say if there's like a superlattice region, and you kind of want to compare sort of the first few layers versus the last layers, it's sort of inevitable that we will get broadening in those superlattice region, but if you still want to make comparisons of either the composition or the dopants within them, you can use the areal density to compare. So, you know, if they are the same, even if it gets broadened, the number of atoms are going to be the same. So if you take the area, if they're the same, the area should be the same as also. Yes.
All right, I take it back to finish it off for the SIMS portion. There are several impurities that we detect to do a root cause analysis. Some of these elements that we see point to a specific problem. It could be a memory contamination or the copper piping contamination and so on and so forth. But in short, SIMS we use for very low concentration of impurities and has a dynamic range from impurities to atom percent. It's a powerful tool for layer structured electronic epitaxial films. We have 50 SIMS instruments in AAG and all 3 spectrometers. We have lots of standards to really calibrate anything that we see that is technologically interesting. So the next topic is about physical structure, physical nature of these elements. And with that, I'm going to introduce you to my partner in crime that I always work with. If the SIMS data doesn't make sense, go to Mike Salomon to get some microscopy data for it to see if we can make sense of it. And Mike, please take it away.
All right, thanks, Tamel. So you've heard a lot about how we can attack problems with very low concentrations of elements and how to understand those in our samples using SIMS. And now I'm going to talk a little bit about how we can address some GaN hemp related structural issues and with microscopy. So what issues can we address? So EAG, not only just microscopy, can help with characterization and FA of the purity of the raw materials that you're using to create your compound semiconductors, to create your GaN and precursor epi. We can also then look at epi composition, doping, contaminants, and structure using SIMS, as we were talking about in STEM, for instance. And then we can go all the way to the device level and look at reliability and field failures and help you try to create some different experimental setups to then look at how potential defects are affecting the reliability. So we can do defect isolation with some optical or electron techniques. We can then also look at the atomic structure and crystal defect analysis using STEM. And then if we need to really look at finite volume of structure with like dopant type sensitivities, then maybe we can try something like SEM cathode luminescence or atom probe tomography, or potentially an AFM technique called scanning scanning microwave impedance microscopy. So next slide. So the next question was, can we make a comparison and then state the trade-offs between different defect characterization techniques? So with that, for structural assessments in like the micron to tens of nanometers range, we can use SEM and dual beam fib to then make cross sections and analyze the structure. And we can even do EDS of these kinds of at these kinds of scales to get a general idea if things are in the right place. For more specific information about the crystallography and the structure and composition at sub-nanometer resolutions, we're then going to need to do something like STEM with EDS or EELS. And then for dopant and point defect level issues with spatially resolved techniques, we can use like cathode luminescence, like I mentioned, or SMEM, etc. And then obviously SIMS for non-spatially resolved dopant level issues. So next slide, please. Oops, it's frozen for me.
The next question, Mike, is what are the typical defects that needs attention?
Okay, so in GaN hemp, the typical defects that we're dealing with day in, day out are typically crystal defect based, so looking for stacking faults, misfit dislocations, nanopipes, and threading dislocations that then go on to form V pits, like Tamel was explaining with the carbon contamination for the SIMS. Sometimes there's etching and regrowth issues, and then gate foot interface issues are a common one as well, where you have potential metal diffusion or you generate algan tears on the drain side of the gate. Then you also sometimes come upon dopant level issues where maybe you have inhomogeneous doping around crystal defects at the gate region or in the channel, along with vacancy populations and contaminants. And lastly, we see a lot of issues related to surface passivation and that interface in the channel, things like delamination, different contaminants, as well as looking at the composition and the bonding of the nitrides, typically the silicon nitride, silicon oxynitride to the GaN surface. So which analytical techniques would be useful to pinpoint gate-induced drain leakages? So for this really depends on device topology. So typically use optical techniques to do this. And so the question really is, can you get light out through the top surface while you're operating the device? Or do you need to go after the issue potentially from the substrate side if you have a transparent substrate such as sapphire or silicon carbide? So if no light out, then you're kind of limited to techniques like liquid crystal, polarized light microscopy, and infrared microscopy to then locate generalized hotspots across the area of the device. And so in these cases, those hotspots are going to be tens of microns big. So they can still be a bit of a challenge to still try to find the specific source of the leakage, but it's doing better than if you had nothing at all, right? And then in the case where you can get light out of either this top surface or underneath, we can use techniques like electroluminescence or emission microscopy, which is known as EMI, or we can use a technique called O-Birch, which is a scanned laser-based technique as well. So next. So morphology contaminants, what are the best techniques? They're asking for a comparison between ECV versus SIMS versus Hall, and how does, I missed the last of the question there, but how can we see? And then how does crystal quality have a large effect on performance? So looking at morphology, dopants and contaminants, as I mentioned, we can use SEM and STEM for the structural assessment. Hall effectively measures carrier type and concentrations, while SIMS actually measures the actual atoms that are present there. So using both of those techniques together can give you a much better picture of what's going on and maybe related to your electrical performance in your devices. And then I mentioned earlier using cathode luminescence. In this case, SEMCL actually has very good sensitivities to small compositional changes as well as dopant level constituents. This is an example on the right showing the case of an ME located hotspot, and then doing a SEM cross section here, we can actually see that the luminescence signal coming from the area around this threading defect underneath the gate appears to have a similar carbon composition to the unintentionally doped surface layer versus the carbon compensated GaN layers deeper down, showing that we have a possible area where we could actually have a short through the device. So this is a very nice way that we can have spatially resolved dopant level information that other techniques can't really get to. And then to answer the question about crystal quality, and then of course the answer to that is yes, but it can be a little bit complex because not all threading dislocations are the same, right? So you have either screw dislocations or edge dislocations, or then combinations of those and mixed dislocation types. And we can actually use STEM to sort those out for you as well. So, and type them. So, and the last question was, if cathode luminescence is used for some characterization, what would be the advantage, if any, on performing the analysis at the device working temperature? And so this is a bit of a complex question, but a pretty interesting one. In our lab here, we've primarily focused on doing CL at room temperature and low temperature, cryotemps, because working at colder temperatures, the luminescence is often 10 to 100 times better than at room temperature, for instance. So you get much more light out of the sample, and the carrier lifetimes are a bit longer. So that gives you access to looking at defect states in the sample. There is typically a blue shift of the near band edge emission in GaN, which you can see over here to the right, as well as a sharpening of the emission. So the full width half max of the emission decreases with temperature. So that allows you to resolve distinct emissions a bit better. And so this gives you access to understanding a bit more about doping level effects and defect structures that would be otherwise not visible at room temperature. So then the concept of doing CL at operational temperatures, which could be tens to hundreds of degrees C above room temperature, there is some evidence that you would end up with more localized emission from defect structures. So you might be able to resolve some sort of thermally activated defects or behavior, which could be very interesting. But overall, you would have potentially lower CL emissions. So signal and noise could be a problem. So acquiring data in reasonable amounts of time might be an issue. At EAG, we aren't actually set up for the high temperature work, but would be really interested to talk to someone who might be interested in doing that and see if we can figure out a solution. So with that, I'm going to turn it back to Alan.
All right. This quick. Sorry, a little bit of delay there. That gets us very close to the our time. So let me just say a few words to wrap up on things. In particular, why choose EAG? In particular, we have a wide variety of good points here. We basically assume non-disclosure with almost all of our clients. So client confidentiality is certainly a core to our business. You can certainly trust us with working together with you. We have many people who are well established in many different areas of science. So we are also leaders in being able to problem solve. With that, also, we have a very extensive knowledge base, lots of skilled experts in a wide variety of techniques, some of them you see here, but also many others. And so that allows us to approach a problem from many different perspectives. you may have heard there's no such thing as a magic bullet. So hence, it is good to be able to use multiple techniques to be able to get a better overall solution, as has also been evidenced, for example, the microscopy and SIMS overlays that we have in this type of study shown here. We can scale our demand with and meet your time constraints since we have so much instrumentation. Basically, surface analysis is what we do. That is a primary portion of our business. So we are ready to be able to scale up to as you scale up. So we have certainly are recognized as a global leader in materials testing and also have high quality. So we're also part of ISO 9001 as well as 17025 quality accreditation. So those also be a requirement for you for doing business. So either way, we are happy and ready and willing to work with you on your problems, and very much looking forward to reaching out to us for whatever you need. And so with that, Rena, I guess you need to have a few last things.
Yes, thank you, Alan. Just wanted to say thank you to all of our experts and thank you everyone for attending today's event. If we didn't get to your questions today, we will be following up with you soon. And if you have any other questions, please send in your questions to the email address on the screen. That is customerservice@eurofins.eag.com. And once you leave today's webinar, you will receive a survey on the presentation, and we would appreciate your feedback. As you see on the screen, we do have upcoming additional webinars. Next week, we'll dig deeper into advanced microscopy for compound semiconductors. We also have 2 more upcoming Ask the Expert events for residual gas analysis and X-ray diffraction. So please be sure to register for our upcoming events. I've placed the links in the chat for your easy reference, so you could just click on those and register on there. And on behalf of Eurofins EAG Laboratories, our experts and moderator, thank you for joining us today and have a great rest of your day.